লাইভ স্ট্রিম আমার থেকে হচ্ছে। বলছি অর্জুন, তুমি ওই জায়গাটা থাকো তো যেখানটা হচ্ছে, ওই স্ট্রিমিং হচ্ছে, যেখানটা পিউপিল অ্যাড হচ্ছে না, ওই জায়গাটা মিউটের জায়গাটাকে মেনটেন করো তো। কেউ বাইরের লোক দেখলে মিউট করে দেবে সঙ্গে সঙ্গে। ওকে। হ্যালো হ্যালো, বলছি যে যেই জায়গাটায় পিউপিল জয়েন করছে ওই জায়গায় যদি কোনো অন্য এক্সট্রা লোক ঢোকে মিউট করে দেবে, সেটাই বলছি। মেনটেন করো, তাড়াতাড়ি যাও। অন থাকো, স্টুডেন্টকে নিয়ে বসবে, স্টুডেন্টদের নিয়ে বসবে।
ওই ভদ্রলোক?
হ্যাঁ হ্যাঁ,
আচ্ছা আচ্ছা,
সব অ্যাক্সেস আছে এখানে, টার্ন অন মাইক্রোফোন, টার্ন অন।
সবাইকে অ্যাক্সেস দিচ্ছ তো জয়েন করার জন্য?
হুম। আর না হলে বইও বাজে, বইও করে দেবে যদি প্রবলেম ওকে। হ্যাঁ ঠিক আছে, তুমি বইও বললে অনেক ভালো তো। ঠিক আছে, যাই হোক। ঠিক আছে ম্যাম। আচ্ছা, আর একটা কথা, যখন মিটিং চলবে ওই রেকর্ডিংটা যখন ক্লিক করবে না, আমাদের সারাউন্ডিংয়ের ভয়েস কিন্তু রেকর্ড হবে, ওই জন্যই সাইলেন্ট থাকতে হবে।
একদম সাইলেন্ট, সবাই সাইলেন্ট থাকবে।
অনলি ইশারা।
তুমি চিন্তা করো না, এর আগে ওয়েবিনারগুলো আমরা জয়েন করেছি,
সেটা বলছি না।
আইডি ব্যাটারিকে বলবো ভিডিওটা অফ রাখতে।
হ্যাঁ প্রধান।
কতগুলো পিপুল হয়েছে? 18? আকাশ এসে গেছে। ওখান থেকে এখানে স্ক্রিন রেকর্ড আর হবে না।
এখান থেকে
হুম,
হলে আমি যখন কথা বলবে আমার এখানে ভিডিওটা হবে।
এখানে রেকর্ড করা যাবে না, এখানে অলরেডি একটার উপর লোড চলছে।
তিনজনকে তিন জায়গায়
এটার সঙ্গে কোনো আমি এখানে মাইক্রোফোন অন করবো না, আমি তো কথা বলছি না, আমরা তিনজনে তো কথা বলছি না, তাহলে আবার কি আছে? হুম। নোটিস করো তো স্যার জয়েন করছেন নাকি। স্যার 35-এ আছে। হুম, 30-25।
হুম, 3-4-5 ঘন্টা। আমাদের সেট আপ করতে টাইম লাগে।
ধরে রাখো বুঝলে,
হুম,
এইগুলোতে যাতে সেটাকে একটু সবাই ধরে রাখে, ওনাদেরও কিছু বেনিফিট মনে হয় কিছু বিষয়ে, একটা সার্টিফিকেট অ্যাটলিস্ট
এসে গেছে এসে গেছে এসে গেছে এসে গেছে। রেকর্ড স্টার্ট করো, আমি অ্যাক্সেস দিচ্ছি। হ্যাঁ, এক মিনিট এক মিনিট, আমি অ্যাক্সেসগুলো দিই।
Hello, everyone. Can you hear me?
Yes, sir.
Yes.
But you are not visible.
I'm not visible. Uh, Wait a sec. I should be visible, but
জিমো করলে ইউটিউবে লাইভ স্ট্রিম হবে না।
I have not used Google Meet in quite a while, so maybe there is some technical issue in this. Uh,
Sir, you are visible, but there is a background for that virtual background. For that, you are not. Your face is not visible. The virtual background is covering that.
I know how to I get rid of this virtual background.
কারণ এটা পপ আপ হচ্ছে না, আটকে আটকে যাচ্ছে,
I'm
অনেক আগে স্টার্ট হয়ে গেছে।
just a sec. Any? Am I visible now? No.
এক মিনিট।
Sir, no, sir. Do one thing. When you hover around your screen, there is a middle option that is telling apply visual effects.
আমি যদি এখানে
Can you find that?
আমার তো মিউটই আছে।
1 sec.
হ্যাঁ, শোনা যাচ্ছে তো।
Sir, no, sir. Do one thing. When you hover around your screen, there is a
Apply visual
middle
effects.
option.
Yeah.
Yes, sir. Click on that,
Yeah.
and so there is one option there above appearance, square type, double square option.
One sec. Uh, I yeah background.
Backgrounds, filter, appearance. There are three options.
Yeah, yeah.
Just above option, above appearance,
Uh
there
huh.
is a diamond shaped option.
Yeah, yeah, yeah. Okay.
Yes, click that, and there
Uh,
will get, I guess, remove all or something you can get.
yeah. Remove all.
Yes, the background has been removed, but your back, it is very dark.
Uh,
Matlab, yes, your video.
reason.
Yes, sir. Now you are properly visible.
But
Your video has stopped.
one.
Yes, sir. Yes, sir. Now you are properly visible, sir.
Okay. So now we can start.
Yes, sir.
Okay. So good evening, everybody. I'm first of all, let me express my gratitude to Talisha Aerospace, Mr. Vaibhav Sarkar, Akash, and the others team members to invite me to do this webinar on a very interesting topic of advancements in aircraft. What is the latest things that are happening in aviation for as far as aircraft is concerned. That means in airframe, in engines, in fuels, all over. What are the latest things that are happening? So now I have a presentation, but there is one presentation given to me by Talisha, which is basically 4 or 5 slides of the history in aviation. So I can ask Akash to just share that. We can go over it quickly and then do the presentation that I have prepared.
আমারটা ব্যাগ কি করে হলো?
কেউ কলটা সুইচ করে দিয়েছে।
Wait a sec, sir. Seeking the permission for presentation to the
Yeah, sure.
Meet admin.
No problem.
A very good evening to one and all present over here. It is
কে মিটিংটাকে সুইচ করছে? এই জন্য এদেরকে ওদের বাচ্চাগুলোকে
us today the respected chairman, respected MD, and respected CEO of Talisha Aerospace. Your leadership and vision continue to inspire all of us, and we are grateful for our unwavering support in making this event possible. Mr. Sharma has been a remarkable leadership in the field of aeronautics, and his contributions have significantly shaped the industry. We are truly honored to have him with us today to share his insights and expertise. We are confident that today's session will be enriching and provide valuable knowledge to all of us as we continue to explore the fascinating world of aerospace. Thank you, Mr. Sharma, for taking the time to be here today. We look forward to your presentation and the engaging discussions that will follow. Once again, a warm welcome to everyone, and let's make the most of this opportunity. It's an honor to stand before you today and share the vision and mission of Talisha Aerospace, an innovating and dynamic private space research organization from India. Established in 2024, Talisha is dedicated to pushing the boundaries of space exploration by focusing on reusable rocket technology, CubeSats, and space exploration itself. Our mission is clear: to develop India's capabilities in resourceable space technology, enabling a sustainable future for space exploration. We believe in fostering collaboration between students, mentors, and industry experts. At Talisha, we empower students to create innovative and creative solutions to globe space challenges. Through hands-on learning, students have the opportunity to build cutting-edge technologies while competing on the global stage. Our ultimate goal is to tackle global space issues with a key focus on developing low-cost payloads to make space exploration accessible and affordable for all, particularly for startups and the research community. One of the most exciting projects we are working on is the Kalpana mission, which will be launched by 2026. The mission marks a significant milestone for Talisha Aerospace, as it will demonstrate for our advance in space technology and pave the way for future endeavors that push the limits of space exploration. We are proud of our journey so far and are committed to counting our efforts in shapes the future of space exploration, making it more accessible, affordable, and sustainable for generations to come. Thank you. Now,
I'm presenting.
Oh no.
Sharma, are you there?
Yes, I am here. I am waiting for the presentation to come up.
Okay. So I'm just requesting you, please stage is yours.
Right. You can go to the next slide.
Is it presenting?
Yes, it is there. We can see it. Just go to the next, make it full screen and then go to the next slide.
Okay, sir.
Right.
Yes.
So this brief.
Wait a sec. Doing it. I can full screen it by this, so that would be better. Now it's good, I guess. Now it is full screen, I guess.
Yes, it is. So this gives the early aviation history, the jet age, the advancement in design, modern commercial aircraft, military fighter aircraft, future aviation challenges and considerations, and conclusion. Next slide. So what is an aircraft? An aircraft is a vehicle that is capable of flying through Earth's atmosphere. We all know this. And a vehicle such as airplane or balloon for traveling through the air, airplanes, hot air balloons, helicopters, anything which is heavier than air is considered to be an aircraft. Of course, we have another branch of things that go up in air or space, which are the lighter than air systems, LTA systems, which is not the topic of our discussion today. Next slide. So the classification is based on the lift generation and design configuration. So you have, as I said in earlier slide, heavier than air and lighter than air. So you have HTA system and LTA systems. And in there, in the heavier than HTA system, we have two types, that is powered ones and non-powered ones. So in the non-powered ones, we have the gliders, which are known to everybody else, and as well as kites, which the kids fly. And the powered ones have then, many variants like fixed wing aircraft, vertical takeoff and landing, ornithopter, rocket propulsion, rotary wing, which is the aircrafts, helicopters, what we call them, and so on and so forth. And in lighter than air systems, again, we have powered and non-powered ones. The powered ones are the airships. The famous airships were in the 1930s, when the lighter than air systems were more prevalent in air transport than the heavier than air systems. It was the unfortunate accident to an airship called Led Zeppelin, which brought an end to the lighter than air system air transport. And after that tragic accident in which 30 plus people were killed, the industry shifted its focus from lighter than air systems to heavier than air systems, and that is when the aircraft, which had already been flying in the 20s and 30s, they came to the fore, and then they took over from the lighter than air systems. In the non-engine category, in lighter than air, we have the balloons and kite balloons, etc. So this is a brief classification of aircrafts. Next slide. Next. Right. So where does the inspiration come from for man to go up in the air? It's from birds. Man has been seeing birds flying overhead from the inception of our universe, and that prompted man to that it should also go and fly. And there are legends in the Greek mythology, and where a person called Icarus, he used wax to attach wings to his arms or his shoulders, and then he took off. The legend says that he went up in the air with those wings which were fixed with wax to his shoulders, and when he went too close to the sun's heat melted the wax, and because of that the wings separated from, and then he fell down to the earth. So this is just a legend, but this just goes to prove that humankind or mankind has been thinking or has been desirous of flying in the air, seeing the birds fly in the air. Next slide. So the next important dates is in the mid 15th and 16th centuries, when Leonardo da Vinci made some drawings which which look like the flying things which can go up in the air, but of course no model or nothing survives to this day which can prove that whether any model was created based on Da Vinci's drawings or not. So we are not aware, but at least we can be certain of one thing, that humankind or mankind has been thinking of aircraft and flying in the air right from its inception. So from the Greek and Roman legends, which I just recounted, the legend of Icarus. In the 15th and 16th century, the Italian Renaissance people were also thinking in terms of making contraptions or machines that can go up in the air. Next slide. So the next important dates in the 18th century, towards the end of 18th century, when two French brothers, Montgolfier brothers, they made a hot air balloon, and it was called Aerostat Réveillon, lifted off with no passengers. There were no passengers, but it attained the altitude of about 6,000 feet. So that is the first recorded effort of balloon going up in the air. Next slide. So then let's come to the powered flight, because balloons are non-powered or unpowered. The powered flight started in the early 20th century, the beginning of 20th century, and the first to go up in the air were Wright brothers, Orville and Wilbur Wright. They made their aircraft called the Wright Flyer, and based in Kitty Hawk, North Carolina in USA. And I believe the decision that who will go up in the air first was taken by the toss of a coin, and it was Orville Wright who won the toss, and he was the first man who piloted an aircraft. So Orwell piloted the aircraft for a distance of 120 feet in about 12 seconds, which was the first powered flight recorded in the history. Next slide. So then the jet age came towards the end of Second World War. 1944, 1945 was the year when the first jet fighter, Messerschmitt Me-262, it flew. But it was too late to make any, difference in the outcome of the World War. But the Germans were the first one to take the lead in jet-powered flights. And once the war ended, the jet engine concept took hold, and the industry then started making civilian aircraft powered by jet engines. And the first jet engines were installed on aircrafts like Comet. Rolls-Royce was the leaders, Pratt and Whitney, as well as Rolls-Royce. So they made the jet engines in the 1950s, early 50s, and early 60s, which powered the then jet-powered aircraft. The most successful jet-powered civilian aircrafts were Boeing 737, Boeing 707, which Air India had in its fleet. 737 Indian Airlines had in their fleet, and de Havilland Comet was also jet-powered, and Boeing 707, and then it went from strength to strength, from Boeing 707 to 727, 737, 747, etc. The size grew, the range grew. Maybe the earliest aircraft were about 4 or 5 hours of range. Then 707 could go transatlantic, trans-Pacific. It could cross the Atlantic and the Pacific Ocean. So it's 7 to 8 hours became the range for these aircraft. And then by the time 747s and by the time Airbus 330s, 340 and 380 came up, the range has now become, huge. It's an astronomical 16, 17, even 18 hours. The aircraft can fly without a refueling stop. So it both in its range and its size, the civil aircraft have, achieved quite a lot of success. Next slide. So 20th century and beyond witnessed remarkable advancements in aviation technology. So the changes that we saw were glass cockpit introduction. So instead of the gauges, which were analog gauges, we had digital systems installed, and that gave way to the CRTs, which is traditionally called the glass cockpit, where all the systems can be presented in a digital format. Then fly-by-wire was another big advancement. As far as aircraft structure is concerned, the composite materials was the next big, change. Instead of metal, the composites were used, and then computer-aided design came on the scene. Boeing 777 was the first aircraft which was entirely designed on a desktop. It was on a computer design, and then the prototypes were manufactured. Supersonic passenger jet like Concorde also operated, but then due to various reasons, including some politics, the Concorde did not have a very long life. It operated for about 10-15 years, and then ultimately the project was shelved because of it became non-viable. But the other big aircraft, Boeing 747, Airbus 380, they have now revolutionized the long-haul travel. Next slide. So similarly, there were a lot of advances in the military side also. New concepts came up, which were like look down, shoot down capability, head-up display, etc. All these were first introduced into the fighters, and then from fighters, it was established that their efficacy and importance. So then they were also used on the civilian side. So like head-up displays were first introduced on the fighter pilots, because the pilot should be relieved of his duties to look at the instrument panel as well as look outside if he's engaged in a dogfight with another aircraft. And so the head-up display projected the essential flight information on his windscreen. So we could simultaneously look at the airspace outside of his window, as well as look at the essential flight parameters like his attitude, etc. So that system head-up display was introduced in the military, and then it was adopted by the civilian aircraft. Next slide. Future of aviation, I will go over in the other presentation, which I am asking Akash now to shift the presentation to the other presentation, which I have shared with you.
Okay, sir. Done.
Oh my god, when hacker meets developer. Next slide. দুটো slide বলবে। Anushka Chaudhary has left the meeting.
Is it okay, sir?
Yes, it is fine. So, advances in aircraft design. In this presentation, I will go over the latest that is happening as far as aircraft are concerned. Brief word about myself. I am an aviation professional, a veteran in aviation, I would say. This is my 49th year in aviation. I started in 1976 as an aircraft maintenance engineer with Air India, and subsequently I became a quality manager for Air India. After retirement from Air India, I worked for another airline called Air Costa, and since last 3 years, I am a visiting professor or professor of practice aerospace engineering at Chandigarh University. I am also presently the chairperson or chairman of the Aeronautical Society of India Bombay branch, and associate director of 3D Graphy, which is a think tank about 3D manufacturing, which my other love besides aviation is emerging technologies. So 3D or additive printing, digital twins, robotics, etc. All these are my areas of interest. So next slide. Okay, so the research areas I have, divided in under four headings: airframe, research in airframe, what is happening as far as the airframe are concerned; power plants, what is happening in the engines; then materials, which is a very interesting topic, what is happening in the material side; and finally the fuels, because the fossil fuels which are being burnt by the aircraft of today is damaging the environment by creating a lot of carbon dioxide and nitrous oxide emissions, NOx, what we call NOx emissions, which is damaging or which is harmful for the environment. So there is a big thrust and a lot of research is being done in alternate fuels. So I will go over what is the latest at the moment in that field also. While I am presenting this, I would like request all the participants, all the attendees to make a note of what I am saying, and maybe think of the questions, their doubts, etc. Note them down, and when we have the question and answer session at the end, then you can ask your questions one by one. Because otherwise, if you do not have, formulate your questions now, then a lot of time is wasted by, at the end. So as I'm going over these slides and explaining the advancements, you can note down your doubts or comments and then ask them in the question answer. Next slide. Okay, on the airframe side, I have three topics to discuss. Number one is the wing design. Number two is foldable and active wing tip fences or winglets, as we call them. And number three is the futuristic materials that are being used for construction of the airframe or the aircraft structures. Next slide. Okay, so in the wing design, the most important presently is the blended wing concept, which is already existing in the military side. As I said earlier, the advancements almost always take place in the military side or the defense side, and then they are once they are proven there to be successful, then they are used on the civilian side. The reason for that is that civilian side there are a lot of funding issues. Funding is not easy to come for research, and aviation research costs a lot of money. It's in billions of dollars, not even millions, it's in billions of dollars. So whereas in defense side or the air forces of the world, money is not a consideration. So if there is a blended wing design which will help USA or Russia or China or India to to launch an aircraft which will help in defense preparedness, then money is no consideration. So that is how the blended wing is already existing in the military side. So we have the US stealth fighters, which is a blended wing design. It looks something like what the picture you see in front of you. And there are a lot of advantages of that. So this is now proven on the defense side that it is a viable design, and it offers a lot of advancements or advantages over the traditional swept wing or cantilever wing with a dihedral angle, the ones which we have on Boeing 747, Airbus 380, Airbus 350 aircraft. So this blended wing is now finding its way into the civilian side. So a lot of research is being done by both Airbus and Boeing, and this is just a representational photograph. So if there is tomorrow a blended wing commercial passenger jet, it will look something like that, whereas the fuselage seamlessly blends into the wings, and that is why it is called. So it's essentially it's a wing which is flying. So the entire aircraft is basically a wing. So it gets all the advantages of the aerofoil construction of the wings, which gives the lift of the aircraft. At the same time, the same structure can carry passengers and cargo within itself, and that is why the aircraft or this concept is called the blended wing design. So this is a lot of research is being done, and maybe within the next 5 to 10 years, we might have a blended wing commercial jetliner flying successfully flying. Next slide. So this is another revolutionary air wing design, which is called a circular or a ring or endless wing. So as a matter of fact, what actually has been done is that the wings have been folded upwards both sides, and then they have been joined at the top. So this was a Lockheed design. Lockheed had made an aircraft with this design, which is called Lockheed ring wing aircraft, and a lot of flight testing has taken place, but there are still a lot of issues which have not yet been sorted out. And as I said, the funding is an issue in the civilian side. So whatever funding was available has been utilized by Lockheed to make it for further research is at the moment not keeping pace with the design concept. So there are certain issues like boundary layer, addition of boundary layer, etc. These issues are not yet sorted out because a lot of funding is required to do further research on that, so that it can be proven that despite its inherent advantages of no loss of lift from the wingtip, because on the wingtip, and there are no wingtip vortices which create drag on conventional aircraft design. Since there are no wingtips in this, there are obviously no wingtip vortices. Wingtip vortices elimination means that drag due to wingtip vortex is also avoided. So, so there are some inherent advantages in this design, but the question is that if this is such a great idea, then why it has not taken off? The answer for that is that the complete design approval, etc., is based on the manufacturer proving it to FAA or the aviation authorities, EASA, etc., that this design is better than, and then to the airline companies that this design will be much better than the conventional design. Fuel savings will be there, etc. So, unless that can be done, no airline will, go for this aircraft. And since that has not yet been proven, so that is why this design still remains on the drawing board. But this is one of the revolutionary things that has come up. Next slide. So this is how it looks in the plan and the frontal views. It's basically a ring, so that is why it is called ring wing, or a circular or an endless wing, because there is no wing tip. Wing tips are not there, both the tips are joined together. So, and this is how it looks in the side view on the other side. You can have a look at it. Next slide. Right. So the next advancement that is taking place is called active winglets. Now, we are all aware of the winglets on the aircraft. We have winglets on Boeing 737, Airbus 320, 321, Neo, 747. All the modern aircraft have winglets, and the advantages are obviously that it results in fuel savings. But that winglet which is there presently on the aircraft is a passive winglet, meaning it's a fixed winglet. Once it is installed, you cannot change the shape or the or the angle of that winglet. Now, as the aircraft design has taken its cue from the birds, and the bird wings in flight, they change their shape at the wingtips. If you see a bird flying, the wingtip changes its shape during the flight of the bird. What flight the bird is going to take, what maneuver the bird is going to do, it changes its wingtip shape. Now, if we have to, and that is the most aerodynamic because nature has made it that way. So, if we have to replicate that on an aircraft, we need not a passive but an active winglet. That means the winglet should be able to change its angle and its maybe the size it is exposed to the airstream, etc. during the flight for different maneuvers. At different maneuvers, it can change. So this is the new concept which is there. There is a company which is producing this, which is called an active winglet or active wingtip fence, as against the passive winglet which is installed on almost all aircraft. Next slide. So these are the three elements of this winglet itself. Then there is a wing extension at the forward end, and there is a load alleviation technology called Atlas technology, which is at the rear end. So all three put together make active winglet, and the manufacturers or the designers have proven on the computers by computer projections that there are significant fuel savings because of an active winglet or active wingtip fence. However, it is yet to be proven on a prototype on a flying aircraft. So efforts are on at the moment to install these active winglets on Boeing 737 or Airbus 320 aircraft. And once somebody manages to do that, then there will be a lot of flight testing will be done to establish that there are real-time fuel savings because of this design. And once that happens, then this will be obviously adopted by the entire industry, and the aircraft which are already flying will be retrofitted with an active winglet, and the new aircraft which will be manufactured will have an active winglet instead of passive winglet. So this is a work in progress, but this is the new advancement which is happening at the moment in as far as wing design is concerned. Next slide. Right. So the next topic to be discussed is about the materials or the aircraft structural materials. So here the new concept that is being worked on is presently is called thermoplastics. The acronym for that is CFRTP, which stands for Carbon Fiber Reinforced Thermoplastic Composite. Now we are all aware of CFRPs, that is Carbon Fiber Reinforced Plastics, which has been introduced with Boeing 777 and Airbus 380, Airbus 350. 90 to 95% of the aircraft structure is manufactured from CFRPs, which is essentially carbon fibers in resin. So the carbon fiber layers interspread with resin material, are used to build up the wing. It has got significant strength to weight ratio advantages over the metal airframe. So that means there will be considerable fuel savings, and everything these days in aircraft design boils down to fuel savings, because fuel is very expensive. Any airline's total expenditure, if you see the pie chart, 25 to 30% of that pie is expense for the fuels, and fuel costs keeps on going up sometimes due to factors which are beyond the control of an airline. Ukraine conflict, or there is a conflict in Middle East, the fuel prices go up. Because of that, the airline overnight, the airline's expenses mount immediately because of the fuel price going up. So fuel price is a very sensitive topic in aviation. So every designer, whatever he is working on, whatever research he is doing, uppermost in his mind is the fact that he has to reduce the fuel cost. And one way to reduce the fuel cost is if you reduce the weight of the aircraft. And when you have CFRPs, they reduce the weight of the aircraft. The strength to weight ratio is better for them than the metal airframe. So that is why CFRPs came on the scene. But now CFRPs have some distinct disadvantages, and one of them was that the repair and etc. is not very easy. Initial cost of producing CFRP structures is higher than metals. So those were some disadvantages. But despite that, CFRPs had been adopted by the aviation industry. But now the new research is being done in thermoplastics. So we have introduced polymer into this CFRPs. So it becomes, instead of CFRP, it becomes CFRTP. That means carbon fiber reinforced thermoplastic composites. What are the advantages of this over the conventional carbon fiber? That is, these can be molded at very high temperatures, and it solidifies on cooling. Now, the advantage of that would be that one is that the weight of the fasteners, rivets, and millions of fasteners that are used will be reduced, because if you can mold a wing or mold a fuselage section, mold an empennage section, then you don't have to attach it with fasteners and rivets. So that weight saving is there. So that actually results in 10% structural weight saving. It has been proven actually at the moment Airbus has a research team working on one fuselage section in Germany, in Hamburg, where they are working on CFRTP, and they are doing some tests on that section. So there they have established that there is 10% structural weight saving by using CFRTP as against the conventional CFRPs. So how do you then attach various things if there is no rivets or fasteners? So you can use ultrasonic and or laser spot welding instead of rivets or fasteners. And the biggest advantage they quote for CFRTP is that it is reusable and recyclable, because CFRPs are, they increase the plastic waste. Once it is discarded for whatever reasons, there is moisture ingress or it gets damaged, then it cannot be reused. It has to be thrown away. And so it increases the, plastic waste. Whereas something that can be molded can be reused. So this becomes environment friendly. So now the two factors which are, moving this idea ahead are, one is environment friendly and second is fuel savings. Because of the weight reduction, the fuel savings will also occur. So fuel saving as well as environment friendly is so. But it's still under design. Research is going on. Maybe in coming 4-5 years, we will have thermoplastic aircraft structures. Next slide. Next slide, Akash. Okay. Go back. Okay. So the next, this one right here. So the next important concept is self-healing materials, which sounds very futuristic and very, sci-fi. Self-healing materials are those that imitate living organisms in respect to their remarkable ability to heal themselves when they are injured. Or for aircraft, we will use damaged rather than injured. It's like the human organisms when you get a cut or on your finger or somewhere, the body heals itself. So that kind of materials are under development, which will in the aircraft use when there is a small nick or a dent or small tear due to hitting a ground vehicle or something. That these materials have the capability of healing themselves, meaning the damage will be repaired by the material itself. So no extra repair will have to be carried out by the aircraft engineers and technicians. So this is another area of research which is going on. Next slide. So self-healing materials are again composite materials, and the four types which are being at the moment being researched are polymer matrix composite, ceramic matrix composites, metal matrix composites, and cementitious composites. So all these four are supposedly self-healing composite materials, where if there is a small damage, obviously if there is a big damage, there is a separation of the wing from the aircraft or some such thing, there is no question of self-healing. But the small nicks and things that happen because of a bird hitting or because of a loose stone from the runway, hitting the fuselage or being underside during takeoff run, those kind of small damages can be healed or repaired by the composite material itself. So no additional grounding or aircraft will not have to be grounded to do that repair. So this is what the latest in airframe materials is. Next slide. Right. So next we move on to the fuels. What's happening on the fuel side? So we have basically four areas of research at the moment. And all this has been necessitated by the fossil fuel which we are using at the moment, that is the jet fuel on our aircraft, is harming the environment. So the emissions, carbon dioxide and the NOx emissions, they are harming the environment. So that is resulted in search for alternate fuels which will not harm the environment, or the harm will be less than what it is for the fossil fuels. So the 4 areas where the research is going on, number 1 is the electric propulsion, which everybody must have heard of. And then we have the SAF, which stands for Sustainable Aviation Fuel. I will explain what that means. Then there is hydrogen propulsion being thought of. And then there is hybrid, which is combination of any 2 or 3 of the above with or without conventional jet fuel. So you have hybrid of electrical propulsion and sustainable fuel. You have hybrid of electrical and hydrogen, hydrogen and SAF, with or without conventional blend. So you may have a design where there is a small jet engine which is burning conventional fuel, which will be used for maybe takeoff or any time the aircraft needs extra power for climbing, and during cruise then it will use electrical propulsion or the sustainable fuel or hydrogen, etc. So all these possibilities are being worked on. Next slide. So electrical propulsion at the moment, the best candidate is the lithium-ion battery. So instead of jet engine, you have electric motor which rotates the propellers, and that motors is powered by the lithium-ion batteries. But so far, it has not been possible to fly the size of a Boeing 737 aircraft or even ATR 50 to 70 seater aircraft with batteries for a considerable length of time or considerable distance. Electrical propulsion is presently for very small single seater trainer aircraft and maybe a few of them with 20 seater aircraft, but they have still not come up with something which can replace the present passenger jet aircraft with jet engines. What are the challenges? The challenges is the energy density. Now, energy density is watt hour divided by the by kilogram or by pounds. So this density needs to be the figure needs to be 500 plus for it to be viable for ATR or 737 size of aircraft to fly successfully. The best batteries available today, the Tesla car batteries, have achieved the energy density of 250, 260, maybe 270, 280. That is the best that is available. So we are at 50% of what we need for successful electrical propulsion. So it will take a long time because unless there is a revolutionary new battery which comes on the scene, lithium-ion battery along with various, it has got variants. There is a cobalt variant, there is a couple of other variants. They have all been used, and the maximum density achieved has been 260, 270, 280 watt hours per kilogram, which is not viable. We need 500 plus energy density to make the aviation viable. So that is a challenge. Then weight of the battery itself is a challenge because, as I said, that weight is everything on an aircraft. More weight, more fuel burnt, meaning less profit or no profit for the airline. Then lithium-ion battery has an inherent disadvantage of a fire risk. It is highly inflammable. There have been aircraft crashes where lithium-ion batteries kept in the cargo compartment, being transported in bulk, have caught fire, and as a result, the aircrafts have crashed. So it is not a very safe as far as fire is concerned. The charging time also is a challenge. It doesn't charge in quickly. It takes 10 hours for the battery to be charged. So that will force the designers to keep additional batteries on board or ground the aircraft, bring it on ground, replace the battery with a charged battery and take off again. So losing the advantage of non-stop flying, etc. That is another challenge. And another final challenge is of the temperature sensitivity. Lithium-ion battery performs very well within its design range of temperature. If it is designed to work between -10 to +20 degrees or 30 degrees, then in that range it performs optimally. However, outside that range, it degrades very quickly. And we are aware that the aircraft, it takes off from Alaska and Siberian airfields where the temperature will -30, -40 degrees, and it goes into Kuwait, Celsius. So in that range, the lithium-ion battery so far is not proven to be very successful. So these are the challenges with the electrical propulsion. So we are not there yet. A lot of work is being done, but it will take a long time for, at least I don't think so. I will see in my lifetime aircraft the size of Boeing 737 or Airbus 320 flying with the electrical propulsion alone. There can be a hybrid, I can accept that, but not alone on electrical propulsion. We are far away from that. Next slide. So the next kid on the block is sustainable aviation fuel. What is sustainable aviation fuel? It is a mix of fossil fuel, which we all are aware of, kerosene, petrol, diesel. These are fossil fuels mixed with the synthetic or organic components made from renewable feedstock. So you have a mixture of fossil fuels and the synthetic, so that will reduce the cost of the, may not reduce the cost, but it will reduce the environment damage. Because if the fossil fuel per unit, per kilogram is producing so much of carbon dioxide, if you are using 50% of that fossil fuel and the rest is organic or synthetic, which is not producing any carbon dioxide, then you are reducing the carbon footprint. So that is the reason why sustainable aviation fuels are being worked at the moment. Now that renewable feedstock could be used, cooking oil, could be fats, plant oils, municipal, agricultural, forestry waste, etc. So these are the various things. There is one plant called Jetrofa, which can be used to produce fuel, which can be then mixed with the fossil fuel to make sustainable aviation fuel. But that Jetrofa has to be grown, so you need a lot of area, lot of farmland to grow that plant. And then you have to harvest that, take it to a plant and convert it to fuel, use the extract of that, and then mix it with it. So these are the challenges which is there. At presently, the best aviation SAF that is available, Airbus industry is working on, it is 50-50. That means it is 50% fossil fuel and 50% of the synthetic or organic component. By 2030, it is they are claiming that it will be 100% sustainable aviation fuel. But that also will not be good enough because the as I will tell you in the next slide, we are far away from our target of reducing or removing completely the jet fuels. Next slide. So various types of sustainable fuels. HEFA is hydro-treated esters plus fatty acids. This is one of the sustainable aviation fluids. Then there is alcohol-based sustainable, that is ethanol and isobutanol, where we remove the oxygen and then you combine the molecules to make fuel. Then there are e-fuels. Now the challenge that I was mentioning is that in the year 2022, the industry, the entire world has produced 300 million liters of sustainable aviation fuel, 300 million liters, which was doubled last year, or in 2023, it was doubled to 600 million liters. But if you see the last line, this 600 million liters is just 0.2% of the total fuel that is required by the aviation industry. All airlines, Air India, Emirates, British Airways, Lufthansa, etc., Delta, United, for all their fleets and the business jets, they all put together, whatever the jet fuel is used in 1 year, 600 million liters is just 0.2% of that. So imagine if you have to completely replace the jet fuel with the sustainable aviation fuel, it is going to take a lot of, and you require not only industry, you require the participation of the countries, political parties, governments, because the feedstock has to be grown somewhere. You need farmland. So the dilemma would be whether you produce rice, wheat and maize for people to eat, or you grow Jetrofa to make sustainable aviation fuel. So obviously the priority would be to grow food grains for people to survive. So in that this SAF will lose out. So I don't see SAF becoming a major factor or a quantum change in aviation industry, though a hybrid fuel or hybrid propulsion That means you remove as much jet fuel as possible, and substitute it with the SAF. That will happen slowly, and the percentage will keep on increasing, thereby reducing the carbon footprint or the environmental damage bit by bit. But to completely use sustainable aviation fuel in aviation, again, it will not happen in the next 30, 40 years, in my lifetime at least. Next slide. The next alternate fuel is the hydrogen, which is very, very promising. The advantages of hydrogen as a fuel is that it has got 3 times the specific energy per unit mass. So per kilogram, whatever energy is produced by jet fuel, hydrogen per unit mass will produce 3 times that energy. So this is a very significant advantage. And the other great advantage is that it is totally environmental friendly, meaning zero carbon emissions. A hydraulic, engine does not produce any carbon dioxide at all, absolute zero. But there are disadvantages. One of the biggest disadvantages is its low volumetric energy density. So you need to carry a lot of hydrogen on board an aircraft for the aircraft to fly a significant distance, 1 hour, 2 hour, 5 hour, 10 hours of flying. And so carrying of that hydrogen on board becomes a challenge. Because you'll need a large tank to carry that, and that will increase the size of the fuselage, which will increase the drag, and you will lose all the advantages that you are getting by burning hydrogen instead of jet fuels. And the other big problem is that you cannot just burn hydrogen in the present jet engine or the present design of jet engines. Jet engines have to be modified to burn hydrogen, and that is not an easy task, because at the moment close to 50,000 aircraft are flying all over the world, of all sizes put together, and they may have more than 100,000 engines installed in that. So you have to change 100,000 engines, which an engine doesn't come very easily. It takes a lot of time to produce an engine. And even if you have a modifier, you have to remove that engine from the wing and then send it to an overall shop for modification. And while that is being done, you have to replace that engine with a working engine on that aircraft, so that aircraft can keep flying. This is not going to happen very easily. So this is another big disadvantage of hydrogen fuel. But the research is going on, and power the batteries on board, and you use electrical motors using the hydrogen as a mover for that. So this is one of the other things which is being worked on, but a lot of work is being done at the moment. Next slide. So one of the alternate propulsion that is being worked on is ultra high bypass ratio GTF, or gear turbofan engines. So this is increasing the bypass ratio to a huge extent. From the present 4 or 5, it may be goes to more than double digits, 10 or 15, the bypass ratio. That means you will increase the blade diameter to a large extent. It will be a huge blade diameter, but that will have its own challenges, because the ground clearance will become a problem. The present wings, they will not be able to mount those engines with huge blade diameters, 12 feet, 15 feet diameter blades. Cannot be, that engine cannot be mounted on the present airframe. So the airframe would have to be redesigned to accommodate that kind of a, blade or that kind of an engine. And the other thing that needs to be done is increase the internal pressure. That means the compression ratio, which presently is 13-14:1 on most of the jet engines, will have to be increased. So once you do that, then you can have this ultra bypass ratio GTF, which will reduce the fuel consumption to a significant amount. The advantages of this ultra high bypass ratio GTF are both in thermal and propulsive efficiencies. Increased thermal efficiency as well as increased propulsive efficiency. The propeller has got a huge propulsive efficiency as against the jet engine. That is why turboprops have the advantage of propulsive efficiency. So once you have a high bypass ratio, a jet engine with a fan which is geared so that it slows down the speed of the fan or the propeller, or you can call it unducted fan. So that will give the both advantages. It will the advantage of the jet engine, as well as it will give you higher propulsive efficiency of a propeller engine. So these put together will be, so there is a research going on this, and let's hope Pratt & Whitney or GE or Rolls-Royce come up with a engine which will be proven to have a better fuel efficiency. Next slide. The other thing that is working on, I think the Pratt & Whitney is working on this called HySight, which is hydrogen steam injected intercooled turbine engine. Now, don't be surprised. This is not a new idea. Steam engine propulsion has been, there for a while, but it was never efficient, or it was never proven successful. So it has not been used so far. But now Pratt & Whitney is, again, their research team is working on this. That is, they are going to use water and generate steam on board an aircraft, and then use that steam to run the propeller or the engine of that. So this is hydrogen steam injected intercooled turbine engine. The advantages are obvious. Steam injection improves the efficiency and power density, and it cuts down the NOx emission practically to zero. So they are nil. And as it, the other thing is that even carbon dioxide emissions are reduced to a great extent. And the only thing is that it, as a locomotive engine, a lot of water vapor is thrown out by that steam engine, and that can cause, again, it can cause environmental problems. So the idea is to evaporate that water in the exhaust of that. But to put something, a condenser in the exhaust is another big challenge. So these are the kind of disadvantages and the biggest one of them is that if you have to generate steam, then you need water on board. So every flight has to carry 30 to 40,000 kilograms of water, and which is not, very light. Water is the weight. So weight will increase again. So again, it will nullify the advantages that you are getting. So the research presently is, trying to have a balance between reduction in weight, saving in fuel, as well as, saving the environment. So this is where the, delicate balance is to be achieved. So every designer who is working is looking at all these things, whether it is an airframe design, whether it is a wing design, whether it is a fuel, alternate fuel, or it is, propulsion, alternate propulsion. Everywhere are the same consideration. Weight to be reduced, fuel burn to be reduced, at the same time, save the environment. That means carbon dioxide emissions and NOx emissions to be reduced or to be eliminated altogether. So that is where the research is at the moment. Next slide. One of the other big idea doing rounds is called distributed propulsion. So instead of two large engines with large, diameter fans or propellers, you put, 10, 15, 20 small engines, and you distribute, and this can also be used for better control of the aircraft. So again, it's an idea still. Research is going on, but as the photograph shows, you can see the photograph. This is what it will look like, which is called the distributed propulsion. Next slide. So there are some other ideas, eco-pulse, which is the distributed propulsion. You saw the picture. And finally, the solar-powered aircraft, where you use the sun rays to generate power to, fly your aircraft. But the size of 737 or even bigger aircraft, the wing needed will be probably 500-600 meters, 1 kilometer long. So it's not viable at the moment unless we can get solar cells, which are 15, 20, 100 times efficient than the solar cells are available now. And with a conventional size of the wing, we can generate enough power to, use the power the aircraft. This idea is also not, but there are some demonstration aircraft where you have a 30-meter wing for a single-seater aircraft, which works on the solar power. And also then the challenges of no night flying. You can only fly during sunlight hours and no flying during monsoon when no sunlight is available, etc. So that is the other challenge. Next slide. Right. So I have finished my presentation. We have 15 plus minutes left. So now is the chance for you guys to ask any questions that you have or give any comments.
Sir, may I stop the presentation?
Yes, yes, you can. And you can ask people to, give questions or ask questions.
Yes. Okay. Utsav wants to ask something.
Good evening, sir.
Good evening, Utsav. Go ahead.
Yes, sir. My question is that what are the challenges that we might arise when implementing a structured design plan for a rocket?
Structure design for a rocket. The challenge there is always for anything which is the rocket would be a fast moving object, right? It will go, Mach 5 plus speeds. So the challenge there is always the skin friction, which creates a lot of heat. And the challenge is to create structures or the materials which can withstand that heat and not, melt or, so that is the biggest challenge as far as that is why you have those ceramic coatings or ceramic tiles on the space shuttle, etc. Precisely for this reason. And the one of the space ship accidents also was as a result of one of the tiles working loose, and it hit the structure and caused a damage, and that then enhanced, and the whole rocket was lost. So that is that's a different kind of a field, different kind of research. It's basically in the realm of metallurgy or material sciences. So basically that is what I can think of.
Thank you, sir.
Welcome.
Divya, you... Okay, Arjun, okay. First Arjun, then Divya, please.
Am I audible, sir?
Yes, you are.
My question is, what are the main goals and objectives of the rocket design plan?
Say again, objective.
Sir, what are the main goals and objectives of the rocket design plan?
Rocket design, guys, this presentation is on aircraft and advancements in aircraft, but you are all asking me questions on rockets and space, which is a different field altogether, and I am not an expert in those areas. So the earlier question was also, but I could answer it from the the general knowledge, from the common sense point of view. But what you are asking me is the goals of rocket design. I can only again answer from common sense point of view that the rocket should be able to reach its destination using less fuel, using a cryogenic engine or what kind of a propulsion system that is there, which is safe. And the other thing, the other probably challenge for rocket designers is to make reusable rockets, reusable re-entry vehicles, as it is called, which I think the SpaceX has proven that they have. Earlier the re-entry vehicle was lost. Once it is used, it was used only once, and then it was lost. It was a waste. Now they have proven, I think, on 2-3 occasions that they can retrieve that re-entry vehicle and it can be reused again. So I guess those are the challenges.
Okay, Divya, you can continue.
Yes, namaste, sir.
Yes, namaste, beta.
Sir, my question is, first is this that the research you are doing right now is about design of the wings.
Yes.
So here a Lockheed design is you are currently working. So is there any other kind of design which improves the aircraft? Like we have Airbus and Boeing, and they have different categories on the aircraft.
Mm-hmm.
So, like every wing is designed according to, like Airbus have their own kind of wing design, and Boeing have their own kind of design. So, is there any improvement currently also that the design of the aircraft's wings?
I can answer it this way, that the present, I mean, when we say wing or designer for wing, we are talking of aerofoil section, right? If you cut the wing, and the section that is available to us is aerofoil, and the Bernoulli's principle ensures that this wing goes up in the air, the lift is generated on the wing. So as a concept goes, there is no change. The design, present aerofoil shape has been optimized, because designers have been working on this for the last almost 100 years, right from 1903 onwards till date. So there is no change in that aerofoil. Whatever the aerofoil today is, that is optimal. There is no basic change in that. So what is the difference between Airbus and Boeing wings, I would say, is the angle of dihedral or the sweep back, or these kind of changes, differences are there. But the shape of the aerofoil design is optimal.
Okay, so here in every aircraft, at the time of designing, we always consider the principle of Bernoulli's theorem. Correct?
Yes.
Okay.
Absolutely.
And the second question is, maybe it would not be considered, but I am also doing a small research on economy of the aviation sector to understand the economy of the aviation sector. As you mentioned earlier, that it is not in million, it's in billion. So can you just brief me current condition of the aviation economy, if you have understood?
If you are talking of aviation economy, I wouldn't be able to give you a one-line answer. But airline economy, I can say that the airlines are not profitable these days. In India, if you think of, except Indigo, all other airlines are loss-making businesses, including Air India. Air India, SpiceJet, Star Air, you name them, they are all losing money. Only the Indigo is the profitable airline. For the reason are different, they had a business model which was totally different from the business model adopted by the other airlines, and they successfully executed their business plan, and that's how they become profitable. And worldwide also, if you see, barring Singapore Airlines, Emirates, and couple of other carriers, the rest of the world's 300, 400 airlines are all loss-making. So airline economy, I can say, is loss-making business, but aviation includes a lot of other things besides airlines, right? So they're like ISRO and DRDO, they are making profit because of the, they are launching satellites for other countries, and they are charging premium or charging for that. So they, ISRO, etc., they are making money. So if you consider total aviation, there will be some areas where there is profit, some areas there are losses. But if you talk of airline economy, it's a loss.
Yes, sir. Okay, thank you so much, sir.
You're welcome.
Okay, Sheetal, you may continue.
Good evening, sir.
Good evening, Sheetal.
Yes, so the session was very interesting, sir.
Thank you.
And sir, I have a question. So starting with, we know that on jet engines we have firewalls and other components to save fuselage from the engine heat.
Yes.
So my question is that, is there a same problem with the hydrogen engine?
You see, firewall is good to contain the fire which is inside the engine, right?
Yes.
If the fire is outside the engine, meaning flames are coming out of the exhaust, and then there is no firewall there, right? You cannot put a wall in front of the exhaust. And if those flames they go upward because of the wind, etc., then above that is the wing, and wing has got fuel in it, right?
Yes.
So the conflagration takes place immediately. So hydrogen is again, it is, flammable, not as flammable as helium was. The earlier airships, lighter than air system, air transports were using helium, which is highly inflammable, but hydrogen is also flammable. So the point is that how do you contain that, fire? That will be a challenge for the designers. That will, again, as I said, that jet engines have to be modified to burn hydrogen. So when they come to that stage that they are modifying that engine, that time they will try to introduce firewalls, so that if there is a fire within the engine, whether it is hydrogen powered or it is fossil fuel powered, the firewall will prevent the flames or fire heat from going into the fuselage and damaging, or the wing, and catching fire. So they will work on that to introduce. But if there is a fire outside, then the firewall is of no use.
Yes, sir. But again, sir, will it be easier in case of hydrogen?
It remains to be seen, and it has to be proven. I cannot second guess today whether the hydrogen fire would be less intense or more containable than fossil fuel fire. I cannot give that answer.
No problem, sir. Thank you so much, sir. Thank you so much.
Welcome.
Okay,
Next.
G. Macquarie, please, you can continue.
Good evening, sir. Good evening.
Good evening.
Audible?
You are audible, but cutting, not very, cutting off.
Your voice is cracking.
Okay, now, sir, now it is fine?
Yeah, better. Tell me.
Okay, sir. First of all, thank you so much. I'm so much educated today in terms of your aircraft designs, which are shown in the future trends in the design of the wing.
Right.
Sir, my question is with respect to the sustainable aviation fuel. As we are looking for the science-based target going to achieve by 2050, 2070, is there any regulation to blend the existing fuels with how much percentage of sustainable fuel for the existing aircraft in Indian aviation scenario?
The regulation is not in terms of what percentage of mixture or what percentage of SAF should be used. It is not in those terms. The regulation is in terms of reducing the carbon footprint or reducing the carbon, from the atmosphere, carbon dioxide reduction. So the regime that is there in place is called CORSIA. You may have heard about it. It's CORSIA, which is Carbon Offsetting and Reduction Scheme for International Airlines. So this is a scheme which has been devised by ICAO, and it is applicable to the entire world, all the world's airlines, so including Air India, Indigo. So the airlines have to, first measure the amount of carbon dioxide that their flights are producing. Like Air India has 100 aircraft and they are flying 10 hours a day. So 1,000 hours of flying in a day. Each hour of flight will produce X tons of carbon. So the total carbon production is, whatever the figure is. Air India will have to offset that by two means. One is to go and plant trees. That is one way of reducing carbon. Each tree takes out 36 to 42 kilograms of carbon from the air. So you have to plant millions of trees. That is one thing. The other one is that you have to buy carbon credits from companies which are doing work in carbon reduction. So these are the two options which are available to the airlines. This will start from the year 2027. And obviously Air India, Indigo, they are not going to go out and plant trees. So what they are going to do is they are going to buy carbon credits from other companies which are in the field of reducing carbon dioxide. And that will add to the cost of travel. So in 2 years' time, 2027, the flight costs, which is there today, will go up by 10 to 20%. So a ticket which costs 5,000 rupees today will become 6,000 to 7,500 rupees in 2027. So that is how the airlines are going to deal with this challenge. There is no target given for the percentage of whatever percentage you have to use, you use. Whatever ways you have to, you use. Make sure that you reduce your carbon dioxide or carbon footprint. That is the challenge.
Thank you, sir, for enlightening on this CORSIA and the carbon reduction scheme from the international sector. So I'm doing my research in decarbonization aviation sector from IIM Mumbai. If I get some occasion, I will come and meet you personally and discuss and share certain ideas. Thank
Sure,
you
you're
for
most
sharing it.
welcome. Most welcome.
Thanks.
So we have one more question, last question, because the time is closing close to 8 o'clock. Subhash?
Yes, yes. Subhash, please continue. After that, I have two questions. I will tell.
Yeah, okay. That'll be the last.
Good morning, sir.
Yes.
Good evening.
Good evening.
Sir, my question is that how the climate is influence the fuel selection that we are selected to for the aircraft?
Fuel selection, I didn't get your question. Can you rephrase your question?
Yes, how the climate influence the fuel that we are selected for the aircraft for flying?
Climate doesn't influence fuel selection. The fuel selection influences the climate, right? If you are burning fossil fuels, then you are producing carbon dioxide and NOx. So, and if you are burning less sustainable fuels, then you are not, producing as much, or you are in electrical propulsion, you are not producing carbon dioxide. So it is the fuel that you are burned that is influencing the climate, if that's what you meant.
I guess he's telling like this ki we have different kinds of fuel like fuel A, fuel B, like that. So which kind of fuel we use at what type of climate?
I mean, Jet A, A1, A4, all kinds of fuels are there. There is high octane fuels. Yeah. So the basically the higher the octane, the higher the carbon dioxide content or the pollution. So the lesser the octane number, the lesser is the. That is a basic. I think it's a linear relationship.
Okay. Thank you, sir.
Welcome.
I have two questions. I'm asking
Yes.
that. First, as we know that B2 Bomber is there, and P21 Spirit that is come recently. So blended wing is something that USA is working on for several decades.
Right.
They have stealth fighter aircraft like SR-71 Blackbird.
That's not a blended wing. That is conventional. SR-71 is a delta wing. Yeah.
Yes.
Yeah.
Delta wing, but it has stealth capabilities.
Yes.
Yes. My question is, India has not developed any stealth capability fighter jet or any blended wing fighter jet till now. How many years do we need? Means how much we are lacking from USA?
Presently, we would be 5 to 10 years behind the leaders, which is USA or even Russia. For that reason, we may be 5 to 10 years, but it all takes the will. It all depends on the will of the nation. If we want it, we can get it much faster, much closer. Like for 60, 70 years, we did not produce a jet fighter of our own. In 1960, we produced a Hindustan fighter. HAL produced a jet fighter, which was HF-24. Marut was the name given to it. And subsequently, the governments, they killed that project, and we were buying our fighters from France, Russia, and USA, etc. for whatever reasons. There were a lot of politics involved in that. But last 10 years, the government of the day decided that we must produce our own fighter, and we produce our own fighter. Now, we have Tejas, which is top-of-the-line fighter, and equivalent to many of the world's top-line fighters. And we are selling it to countries like Malaysia, Argentina, etc. So it has to be good so that the other countries are buying it from us. So it all takes political will to do such a thing. So though we are 5 to 10 years behind, but I'm sure and Tejas and the AMCA, the Advanced Multi-Combat Aircraft, which is the next variant of Tejas, is going to have stealth capabilities. So we are not that far behind. We are a few years behind, but if there's a political will, we can do it in much faster.
But the thing is, that is the main point that you have mentioned. We don't focus on research and innovation in in nowadays, because we just think ki, okay, we will buy it. We have HF, we had HF. Recently HL was developing another thing and the project was trashed again by the government. I don't means The thing is, why do we
Yeah.
buy things for millions of dollars rather than innovate with that same money?
One word answer is politics, you know. And HAL is not a design organization. It's a manufacturing organization. DRDO is a design organization. GTRE, Gas Turbine Research Establishment, that is a design organization. ARD, Aircraft Research and Design, is a design organization. These are the design and research organizations, but they were there all the time, but they were not doing the job that they were supposed to do. But now they are doing it because the politics is forcing them to do it. So it's all a question of politics. If the government of the day decides that we must have a top of the line fighter in the next 1 year or 2 years, we will have it because we have the engineers, we have the brains to do it. It was just the political will that was lacking. Now you wouldn't ask me to go in details of why we were not doing it. That's a different ballgame altogether. But suffice it to say, it was politics. Yeah.
And sir, now we saw that this government has done the space and the aviation sector, privatized it, mainly the space sector only. So now we are seeing Skyroot emerging. We have Tech Mahindra, L&T Aerospace, that is in the defense sector, TASL, Tata Advanced System Limited. So how the private companies will help us emerge in this space race or in this aviation race?
Yeah, that is because when private companies, private sector is open for defense production and defense or maintenance, repair and overhaul of defense assets or for production, then you are utilizing the top of the line technologies that are available with the private players, which are not there maybe in the BRDs, the Air Force BRDs, base research depots. Those, they have a lot of equipment and infrastructure that is decades old, and it's not suitable for producing or repairing the top of the line or the most advanced assets that Indian Air Force has. So how it helps is that the private parties, they have the latest infrastructure, the latest technology available to them. The defense will have the the personnel who are through National Defense Academy or these establishments, whereas the private sector will have people who have done their degrees in Harvard, Yale, or Stanford, etc. So you have a qualitative difference both in the manpower, the intelligence that is available, as well as the infrastructure. So that is how it will help.
Yes, and I also think in the government sector, if we have a company that will be governed or ordered by the government. So if a government wants, then it can trash a project. But in private sector, it is like more or less their own freedom and decision, and they can take that. If they are collaborating, that is different. But
what is in government, what we call it is colloquial or slang red tape, the bureaucracy, the red tape. That is there in any government organ, but it is not there in private. So that advantage will also be there.
Yes, that's a very good perspective to see private sectors as a profitable to this aviation industry. Thank you, sir. Thank you very much for this innovative webinar. Vaibhav sir wants to tell something. He is the CEO of Talisha.
Sure. Yes, Mr. Vaibhav, go ahead, sir.
Hello, am I audible?
Yes, you are.
Okay. So, how are you, sir? How are you doing?
I'm good, thank you.
It's a pleasure, sir, having you within us in Talisha Aerospace. It was an auspicious evening by your grace. Thank you so much. Good evening, everyone present over here. On behalf of all present, I would like to extend my sincere gratitude to Mr. Ashwani Sharma, Chairperson of Aeronautical Society of India, BOM Branch, for his wonderful presentation today. Your expertise and passion for aeronautics have truly enriched our understanding. We are grateful for the time and effort you invested in sharing your valuable insights with us. Thank you once again, Mr. Sharma, for your inspiring session. We look forward to more such enlightening sessions in the future. Thank you so much, sir. And last but not the least, I hope that your gracious presence today in our webinar has enlightened a lot of people who are present over here to foster over the field of aviation for the rest of their lives. Thank you so much, Mr. Sharma. Thank you so much for joining. Thank you, sir.
Most welcome, Vaibhav. It was a pleasure, being here and, making this presentation. And thank you for your kind words. I am always very comfortable and, I am most happy among students. So it was something which I enjoyed thoroughly.
Thank you, sir. Same here, same here. We enjoyed a lot with you, sir, and it was a wonderful presentation, sir. It was just beyond limit. Thank you, sir. Thank you so much.
Akash, maybe everybody can switch on their cameras and we can take a group photo of the screen. If you can just tell everybody to switch on their, Divya, Sheetal, Utsav, Arjun, please.
Yes, sir.
Yes, on your cameras and make that grid formation and then maybe take a.
Okay, sir. Sir will just unpin us three and grid formation will come automatically. Thank you, sir. Thank you very much for this webinar. It was great evening.
Thank you very much. Thank you. All the best, everybody. Thank you.
Thank you, sir.
Thank you, sir.
Now,
is it done?
Yes, it's done. Thank you very much, everyone, for attending it. Thank you very much for attending it. It was a very good session. You can leave now. Thank you very much.
Okay. Thank you.
Abhi, sir? Hello. Photo নেওয়া হয়েছিল?
Akash, leave from this meeting.
Okay.